RISC-V is the protocol by which software talks to hardware. That's what an instruction set architecture is. We heard last December from Qualcomm that they shipped 650 million cores with their Snapdragons already. So when we did vector, we have a bunch of vector for embedded kind of things in there, but it's just a start. This is big. This took 2.5 years and worth every second we spent on it.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hey, Shaheen, great to be with you as always.
As always, what's cooking today, Doug?
Well, we have a really fascinating guest this week with us, Mark Himelstein. He is Chief Technology Officer at RISC-V International, an organization he's been with for the past 3 years, in fact, 3 years this month. And we thought it would be a good time to get an update on RISC-V and its implications for HPC, HPC-AI. So, Mark, welcome.
Glad to be here.
Okay, thanks so much. We were just chatting. HPC, broadly defined, really has changed fundamentally over the last 20 to 30 years. Broader scope, all sorts of changes on the technology end, of course. And looking at RISC-V, share with us some of your thoughts about how RISC-V fits into HPC, HPC-AI as we look at it today.
Yeah, and I think you are alluding to the fact that HPC isn't just for big honking computers anymore. There are pieces of HPC that span from, as you guys have said, from sensors to supercomputers and used in every walk of life. And as Moore's Law is heading towards an end, although I think its death is probably been prematurely announced, it really is an opportunity for people to do more distributed problem solving and stuff that was embraced 30, 40, 50 years ago by things like weather and defense and stuff like that is finding its way into other pieces. The advent of big data, things like Hadoop and Spark with a K and so on and so forth, they all drive towards this. And so RISC-V is a natural for this for a lot of reasons. One is that there's been kind of an EDA renaissance over the last 15, 20 years around modularity, chiplets, et cetera. Easier to plunk down a bunch of cores, have them work in concert. The software has really evolved to a point where it can take advantage of that. And so with RISC-V, it's kind of become a bit of a darling in the HPC world because of its flexibility, because of people's ability to do what they want to do with it, and because it can be put in a lot of different situations from very low power to very high performance computing. You see a huge amount of superscalers out there. People like Ventana and Sci-Fi are making chips that are competitive, if not even faster than other architectures out there. You see both horizontal and vertical scaling going on. This combination of horizontal vertical, like you have people like Esperanto plunking down 1,000 cores on a single die to both do inference engine stuff and HPC. We saw Dave Ditzel talk at the European conference in June. And, we need out-of-the-box thinkers like that in order to drive the industry, in order to solve solutions. Also, very clearly, European Processor Initiative, the work on HPC, the work on cloud, all the work that Europe is doing in the computing arena. And you've got guys like Luca Benini, who also gave a talk where they're experimenting with RISC-V. So they didn't just take our instructions and use the off-the-shelf vector. They also did some work with streaming instructions and streaming data from memory. And so you see there's just this incredible energy and innovative piece of the industry showing up in all sorts of applications, in all sorts of form factors. Now, be very clear. I mean, if you're doing an IoT kind of thing, a sensor or whatever, the runway to get that out is 6 months or a year. You can do something fairly quickly. When you start going up the stack, things take more time, right? So just the ramp time for, things like disk drives is probably like 2 to 3 years. And, data center boxes are 3 to 5 years. And automotive is believe it or not, because of all the interactions at standards, is probably more like 8 years. So there will be some time as this stuff rolls out. But there's efforts going on in every single corner of computer science to integrate RISC-V not only in traditional computing, but in what would traditionally be called HPC arenas.
Mark, you touched on one of the questions I had, which is how long does it take? And one of the things I hear in the industry is, look, it took ARM 20 years before they could have a place in the server world. And my take is that, well, actually, that experience is itself going to accelerate the RISC-V adoption because a lot of that work is done already once, and the second time is a lot easier. Are you observing that? Is that what we should expect?
Absolutely. Look, we're very grateful for other architectures. I like to say we stand on the shoulders of giants, and they've gone through a lot of things before that we get to learn from and take advantage of. And ARM is no different there. They also did a lot of work sequentially, right? So they did a lot of embedded IoT kind of based stuff in the 90s and, worked their way up. And now, there are supercomputers and other things based on ARM processors, laptops, et cetera. The difference about RISC-V, because we watched all that occur, because we watched everything that occurred with x86 and Spark with a C and PowerPC and, MIPS, what happened instead was when RISC-V came to be and when it was like really put into the open world and it's an open standard in 2015, 2016, all the work started going on in parallel for the different, I would say, strata in computer science. So yes, there are people doing earbuds and they've already put them out and they're shipping billions of units based on RISC-V cores. But at the same time, you had the effort start for automotive, you had the effort start for data center, you had the effort start for cloud, for HPC. And so it will be a lot shorter than the amount of time it took ARM, but only based on the fact that, anybody with a little gray hair worked on either ARM or x86 or one of those other architectures and are helping us accelerate RISC-V into those areas of computer science.
Mark, you corrected us, or you actually helped educate us, that RISC-V is not, as we often read, open source, it's open standard. What does that really mean? Could you expand on that point?
Yeah, absolutely. When you start talking about something like Bluetooth or Wi-Fi, it's a protocol, right? It's a standard. RISC-V is the protocol by which software talks to hardware. That's what the ISA is. That's what an instruction set architecture is. And we specifically did not go down the path of doing reference implementations or RTL or DV or any of those things that are microarchitecture really dependent. We left that up for our members to innovate with. Some of them have chosen to collaborate together. So there's other nonprofits like Low Risk doing the Open Titan stuff, or the Open Hardware people doing an SoC. There are various entities that are doing what I would call open source hardware versions of RISC-V. We are the standard. We only have one product, its specifications, including some architecture tests and stuff like that. But in general, what we produce is a specification. And unlike open source, which, there's copyleft and all this kind of stuff, and there's actual source that you can download and make it work in your machine, we don't do that. We give you the instruction set and we have you do that. And in fact, we expect you to innovate. And in fact, we allow you to customize. If you want your own set of instructions, we've reserved part of the opcode space for you to add instructions. And so you can have vendor specific instructions, and we're okay with that. That's what encourages a lot of this experimentation and innovation. And what happens over time often is what is today's innovation is sedimented tomorrow. So we've already seen some things that have been added to specific vendors' architectures that they've brought to us now and want to sediment into the standard. So it's really exciting. It's really a different way of looking at ISAs. ISAs have traditionally been bound with the manufacturer of the chip, right? Or with somebody who enables the manufacturer of the chip. We don't do that. So that independence really gives people the chance to innovate. It gives them a feeling of security that we're not going to ever compete with them. There's no favoritism. It's really driven by everybody coming in and wanting to do the best computer science they possibly can do.
Now, when you look to the future with chiplets and tiles already becoming well established, and the idea that you can mix and match IP on the same substrate, that really further dilutes that notion of an ISA being squarely tied to a particular chip. a chip could have all sorts of different ISAs on it, right?
Yeah, and that's exciting. While people obviously have workloads they've been running certain things on for some time, this gives them the ability to continue to do that without doing a forklift upgrade, but still being able to go ahead and add in RISC-V to do some security piece or IO piece. And eventually, if they wanted to do a more significant piece, they do. We heard last December from Qualcomm that they shipped 650 million cores with their Snapdragons already. And they were intending on increasing the number of cores per Snapdragon. So that free flow of ability in the design process enables people to look at things more as a greenfield opportunity for new functions or for auxiliary functions that they want to upgrade. We have the IBM Z folks who are looking at using RISC-V for like next generation boot processing, stuff like that. So it's just a blessing for RISC-V because it enables people to do stuff like that. But even though it's a really easy on-ramp, NVIDIA's got, like, I don't know, like 10 RISC-V processors per video controller now. It's an easy on-ramp, but it also enables people to go and say, oh, they succeeded in using RISC-V for this. Maybe I can use it for that, right? And in the end, the reason why people look at RISC-V and want to use RISC-V is, number one, flexibility. They can do what they want. They can take the base 47 and just do what they want from there, or they can take the full boat of instructions that we've ratified and adopt them. They can customize it and do the things that they want to do. That is the number one thing. But the second thing is, and this is hard to quantify, Shaheen and Doug, Linux built this culture where people felt Linux was their house, right? If there was something wrong, they could fix it. Eventually, they knew it would evolve and get features that were in other OSs already. It was their house. There was a feeling that they weren't beholden to a vendor, to an architecture. They could do what they want. You can't quantify that feeling of ownership and freedom, right? And RISC-V gives people that for the ISA.
I think that's huge. In agreement with you, even a tiny bit of friction is really damaging.
Well, we are not beholden to the same economics that other architectures may be beholden to. And that gives us a lot of freedom and gives our members a lot of freedom to pursue what they want to pursue.
So, Mark, if you look at the HPC community, again, writ large, the commercial industrial aspect of it is typically looked upon as quite different from, say, the academic and the national lab, the large supercomputer center aspect of HPC and HPC AI. And on the academic supercomputer and lab side, it can be characterized as very, very technically advanced, and they are inclined to, working with technology. And one might think that they would have a mindset that would be quite receptive to the RISC-V idea over against, say, the commercial industrial side, which is more interested in rapid implementation. They're not tinkerers, they're not experimenters as much as implementers. They want to get their workloads done. I'm wondering if you have views on the implications, again, looking at the HPC community industry broadly defined, if those are two different kind of market dynamics within HPC.
I certainly believe that they have different on-ramps and they have different requirements. By garnering the research and university community as followers and interested parties, the one thing that does is it enables a software ecosystem. So if the commercial side wants to take advantage of it, they can. The one thing I will say for both is that it is not general purpose computing. It's not like you're running a data center server or a cloud server. Typically, these are very specific workloads. And when you go ahead and you bring an application on, there's a lot of work to optimize it, right? Because part of HPC is performance results. So it's a lot easier to think about moving over to a new architecture when you're not doing general purpose computing. You don't have to test 1,000 applications, right? And because of that, it makes it easier for somebody to go ahead and do a test and go, oh, I ran this workload on RISC-V, with this microarchitecture from whatever, and here are the results I got. And so if you saw some of the results at the European conference, you'll see that they did exactly that. They took specific ML, NLP, HPC workloads, ran things, and then said, look, with with these sets of instructions and this kind of pipe and this many stages and this kind of cache architecture, this is what I was able to get. So I think that the barriers to entry for both research community and for the commercial side of HPC are a lot lower than you might get in running a general purpose cloud server.
Mark, you mentioned NVIDIA, and I was just noting that if I look at your founding members, it includes folks like NVIDIA and IBM, and at the high end, and then Qualcomm, and then Microchip, Espressif. So it is a strange thing that these guys who actually have their own agenda are also prominent within the RISC-V community. What is
Yeah,
their thinking?
well, I mean, I think it's exactly the things I mentioned before. It's the flexibility and the ownership. It's the same argument that people went through when they were looking at Solaris or HPUX or versus running Linux, right? And it, it took them a long time to reach a point of going like, okay, when it moved from like you risked your job to say Linux to you risked your job for not saying, right?
That's right.
I think the same thing is occurring around RISC-V. In 2015, 2016, early adopters, NVIDIA part of them. Our treasurer is from NVIDIA and very strong supporter. Even when they were going through their ARM acquisition stuff, it was very clear to him that there were very clear functions within NVIDIA that made more sense for RISC-V. And that's the way it's going to be, I think, throughout the industry. Everybody wants more and more success, but we do believe that competition breeds innovation. We don't think there will be one architecture in the end, but there probably is going to be one architecture that's going to behave like Linux that people feel ownership for, and it's the first thing they go to for solving certain problems and so on and so forth. It won't be the thing that they use for solving all problems, although there are some people who are going to try to use RISC-V in all areas. And that's what makes it exciting, because it's a really good push inside of RISC-V to make sure that we have an ISO that can support all those workloads.
I remember you mentioning at some point the instructions that your community is developing all the way down to a microcontroller. You could even argue a sensor that is starting to resemble HPC types of instructions, like vector instructions or something that is computationally focused. What is causing them to do that? And how do you see that enabling HPC everywhere, like we started the conversation with?
Yeah, I think that there's two reasons, and I think this has been true whenever you've seen like mothership versus satellites. This has always been true. There's two things that force people to do more computation down the bottom. One is aggregation of data. There's so much data coming in from so many places. The numbers boggle my mind. The only way to really get that data back to the mothership is to reduce it. And so there's a lot of aggregation of data that requires compute power to do. The second thing is there is local decisions that need to be made. You don't want to have to go to the mothership every time somebody says, Alexa, what time is it? Right? And so you need to be able to make certain decisions locally in order to have reasonable performance and reduce network overhead and things like that. So I think those two things really have driven a lot of it. What you're going to see is an evolution over time. As people figure out more things that they want to do down the bottom, there's going to be pressure to put certain instructions in order to support that. So when we did vector, we have a bunch of vector for embedded kind of things in there, but it's just a start. And it's an iterative process. And what will happen over time is people will want more stuff. So, we have a vector SIG that worries about long-term strategy, gaps, and prioritization. And one of the things on its list is a smaller version of vector that can be used heavily in embedded applications. So expect that will evolve. That's why Dave Patterson calls this a 50-year architecture, because of the extension model that we put in. It's easy for us to add new instructions later on. Sometimes, don't even work with each other, and that's okay. Because, for example, we have floating point instructions in integer registers. Great for embedded. You don't have to have a different register set. But it doesn't work with the regular floating point stuff, right? Because there are real floating point registers. So we have F, which is our floating point stuff, and then we have F in X, which is floating point in the integer set. And they overlap. and it's okay. And people know that one's not compatible with the other. Same thing could happen over time with some vector stuff, and it's okay. We will find out over time. We don't have to do stuff before the members want it. We only work on things that the members care about.
Hmm.
But you can start seeing the trends by going to some of our special interest groups of, hey, this is on my top list. And it's on my top list because of this application, right?
Hmm.
We love that. When people come in and want to do something esoterically, we say, okay, go do a custom instruction, try it out, see what happens. But when people come in and say, I have a workload and I need this, that's exciting.
That's excellent. That's a great example of customization that you mentioned before. Now, of course, the moment you say that, it sort of raises the question of compatibility, which you also mentioned, and also sort of allusion to operating systems and the compatibility that they try to. How do you solve that problem within the RISC-V community? What are the regulations, guidelines, the framework that allows you to have the cake and eat it too?
Well, we've been working for 2.5 years on something called profiles. And profiles are a generation of instructions that work together. So if you think of a generation of Xeons or a version of ARMs, these things work together. And we've worked very hard to put together a profile, families of profiles. And one family is targeted towards rich OS, highly capable machines running applications. Now, I'm not going to tell you that's not on your wrist because it's quickly becoming on your wrist as well as in your data center. But it tells you, look, we're running general purpose computing, and we got the set of instructions together. And the reason we did that was so we can then tell the tool change and the operating systems, go after this. Don't look at all those little extensions behind the green curtain. Look at this group.
Hmm.
This is the group that everybody's going after. We have a trademark called RISC-V compatible. We have a set of tests that are evolving that you'll be able to get a compatibility branding against a profile. So the profiles are going to have nice marketing names, and they're TBD. Luckily, I'm not in charge of naming. you, you'd be very grateful. But there will be the first one will be the stuff we did in 2019 that got solidified. That was done by the beginning of 2020, and it will have a name. Then there will be another name for the stuff that probably will be next year. So every 3 to 4 years, you're going to see a major profile release. In between, you'll see minor profile releases just so that the tool chains can catch up, and there's checkpoints and stuff like that. So that's number one is profiles. And the reason we care about it is application portability. Without application portability, there's no software economy. So you want the software vendors to be able to compile to one thing, and given they're running on the same OS style and stuff like that, they should be able to take a binary and run it on multiple implementations that are also profile compatible. This is big. Shaheen, this is like,
Excellent.
this took 2.5 years and worth every second we spent on it. We're now evolving it. So the next generation of stuff, the next major release will have more like the vector crypto, all that kind of stuff, as well as the basic instructions, hopefully, that will be required for Android support. So we're looking very mindfully, very consciously about what goes in these and how they work together. That's the first thing is profiles. Next year, we've been working on profiles for 2.5 years. We've also been working on something called platforms, and that's so you can do something similar to what is done for other architectures, so that if a distro wants to go ahead and be able to be downloaded, and you have to configure it obviously based on implementation, but the same set of bits should work on multiple implementations. That's what it's going to have. And it's based on a bunch of things. The profile itself, the basic hardware, so the SoC components, platform security, how you boot, so the boot runtime services, and platform runtime services, things like SBIs and UEFI and ACPI and stuff like that. So the components of a platform are being worked on right now, and we expect the coalesced platform to be available sometime in H1 24.
Brilliant. Excellent.
Mark, I'm curious when people are initially looking, technically astute people, but they're initially looking at RISC-V. They're asking basic questions. I'm interested in you telling us what those typically are, but also if one of them might be, how does RISC-V stack up, say, against ARM?
Absolutely. And There's sort of two answers to that question. There's one answer, which is how does it stack up against ARM just based on instruction availability? And I think we have a quorum of instructions. We're very compatible with ARM. But the next question is how does it stack up with things like power or performance or stuff like that? That is left to the members because that is microarchitecture dependent, right? So part of the answer to people is that's up to you. I mean, that's your added value. That's your differentiation. And if they want to, they can go to the RISC-V exchange, which is at risc5.org, and see a bunch of companies that are either selling IP or discrete chips, tools that tout specific things. So they could go to a vendor and say, hey, look, I'm interested in this. And the vendors will help them. They can make them custom chip, they can use an off-the-shelf chip, they can sell them IP. All those things are available because we have built that kind of economy around RISC-V. And so there's a lot of choices for people who don't want to do their own. And there's a lot of choices for people who want to do it all themselves.
So, Mark, we have the obligatory part of the any conversation these days, which is AI, generative AI, unsupervised AI, and various forms of it. This has become such a pressure in every conversation that it makes sense to see what different technologies are doing for it. Would you just speak to how AI is playing in the RISC-V community?
Obviously, there are different pieces. There's the conditioning of the data, and there's the inference engine, running the inference engine. And we have efforts by our members in both of those arenas. I laugh because I end up looking back to my past and going like, okay, what are they doing in that part? Oh, this looks like ETL. This
Yeah, right.
and
Exactly. Yes.
but there's a huge amount of data transformation that goes on in preparation for actually running the engine, right? If you take a look at a bunch of the superscalers and other people, they're all talking about playing in that arena. And then you have people who are just doing the inference engine piece. In both of those cases, I think that there's opportunities for scale, for customization, and more importantly, it's kind of a greenfield situation because people are really trying to solve that problem, I would say, more thoughtfully, are starting with a blank piece of paper. So all of a sudden you have all these people out there like, again, Esperanto, Tens Torrent, even people like, who are in mobile kind of arenas like Qualcomm or MediaTek, or all have needs for those things. And so what you see happening is them going back to their drawing boards and going, oh yeah, RISC-V seems like it's going to fit in here and here and here. I don't expect people to go and forklift other architectures out and shove in RISC-V. I do expect as people go to the drawing board to solve a new problem or to solve a problem in a different way or the next generation of a problem, that's when they look at the opportunity to go ahead and adopt RISC-V. And when they see all this work going on in this arena, all the innovation that's going on in the arena, all the flexibility they have, then RISC-V becomes a pretty interesting candidate. Again, I certainly encourage you to go back and take a look at some of the talks at this most recent summit in Europe. And I think like every 10 seconds, we had another AI talk.
Yeah, that's right. That's right. No, we're going to put that link in the article.
Right.
I just think since RISC-V showed up, once I went through the thought process of maybe Spark could have been the same, maybe MIPS could have been the same, it was just very clear that this was going to be a major trend in the industry. So I'm really delighted to see the progress that you guys have managed to create. And it's just been wonderful to see that and to track it.
Yeah, we're very excited. I was an early employee at MIPS. I ran Solaris for Sun. I will tell you that RISC-V for me is the most simple and elegant architecture I've seen for a very, very long time. Because what happens over time is you start building up technical debt and you start building up sort of legacy stuff. And this kind of gave people a chance to clear the plate and create an architecture that sort of naturally does that over time. And that to me is what's exciting because okay, this year's Chat GPT, what's it going to be in 2 years? Is it going to be, this VR driven world that needs response times and blah, blah, blah? Is it going to be some other retail based, interface? We don't know. So we have to create an architecture that can adapt. And that's really what RISC-V is.
Yeah, you've cracked the code there for sure. Excellent.
Well, Mark, very, very interesting. comments. Thank you for the update. Very much appreciate it, and would love to have you back.
Absolutely. Thank you, Mark. It's been excellent as always. Great to catch up. Thank you for making it happen. I know we imposed it on your schedule at a time that's not exactly convenient, so thanks for that as well.
Oh, it's my pleasure. Always good talking to you guys. Thank you.
Perfect.
Thank you.
Take care.
That's it for this episode of the @HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The @HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.